but talk about, we're going to do two things. One is to talk about what we have learned, looking back a little bit. The next thing is we talk about what do you do, and a few examples of what you could possibly do if your machine learning algorithm on some problem don't work, which happens a lot, whether you are in an engineering role or if you're doing your research project somewhere around here, or in the future. And we'll also talk a little bit about the broader implications of, machine learning is not usually the cure for your real world problem. In fact, it could like lead to some real world problems. So let's get into it. We talked about sampling on Monday, so there's a tutorial sheet on sampling posted on Piazza for people's own amusement. We will not be running tutorial next week because I imagine you will all be somewhat stressed from the course deadline, all sorts of different course deadlines and other things. But feel free to ask like the tutors or myself about these tutorial sheets if you want. Right, so, this is the plan reflecting on what we learned on the high level and debug machine learning, communicating machine learning, broader implications, and so on. I would like to motivate what we're going to say with a comic. It's a comic about, well, it was made to illustrate the process of doing a PhD. It's been quite famous in, I guess, the PhD cycles, but I thought it's also a good illustration about the general knowledge acquisition process, right? So imagine the entirety of human knowledge is this big circle or big sphere cut open. Elementary school is here. After you finish secondary school, whatever it's called in different countries, high school, college, whatnot, you're green, you're still pretty well-rounded, but we're body of knowledge have gotten bigger. In the first 2 years of university, our body of general knowledge has gotten bigger, but we've also gained the specialization. So SML is roughly here, where it's a sort of third or fourth year level math or master level course, where it deepens our specialization. And it provides a good foundation for getting to the boundary of, say, the human knowledge around machine learning. So you may say, right, so what is this dark red bit, right? So this is reading research papers. So the relative length of these color bars don't quite matter. So I would argue that knowing SML sets gives a lot of you a good foundation for understanding lots of research papers. Some are particularly dense and might not be ready to grasp, but a lot of them are accessible to you. I hope that's good news. So with that covered off, meaning once you're at the boundary, for example, you spend the first 3 weeks of your honors project reading papers, then you can start pushing on the boundary. I'm not gonna lie, that's hard, and that's what the rest of the PhD comic says. You can go read about it. What we are going to talk about today is this. Well, let's imagine, right? So this is now a high-dimensional, n-dimensional ball. Like we're showing the slice of it in this circle. If we imagine basically SML as this body of knowledge that lives at a certain space, a certain area in this high-dimensional vector space, then what's surrounding it are other related knowledge that we also touched upon. So, for a lot of, so one thing is that the university mathematical preparation doesn't necessarily give us the relevant background. Also, we have some stats, and basically part of the class come with different parts of preparation, right? Probability, like more calculus and linear algebra, matrix calculus. Let's say, just say. And we have been touching upon a fair number of optimization concepts. There are other dots in this space. For example, information theory, we talked about it, but we didn't actually get to use it much. So SML is quite embedded in all of these related disciplines or topic areas. For example, there's lots of the underlying engines of SML are now driven by parallel computation and so on. So if we zoom into this region, then we can now see basically the internal structures of basically different parts of machine learning that we have covered as of this course. So instead of listing them, I'm just trying to maybe put the different concepts that we've seen on the plot, so as to remind ourselves what they are. After this, you can ask me questions or tell me whether I've made much sense or not. So on the bottom, I would say are the foundations and things that are mainly in chapter 2 and appendix. So I would say vector and matrix calculus. That for some of you is probably not new, especially for those of you who have taken IML. Although some of the results we know are not seen before, that's not surprising, just look them up. So we looked at probabilities with some new depths. For example, you probably haven't seen as much high-dimensional, like multi-dimensional Gaussian distributions and conditioning on it before this class. And now you're expert on it. We touched upon decision theory very shallowly. We also touched upon information theory. It's such a cool topic that I hope you might consider taking the information theory class. That's actually semester 2, right? And we talked about optimization, like basic concepts on optimization. In particular, we have used and talked about convex functions a number of times in a number of different places by reasoning about local geometries, meaning neural network is not convex, but talk about close to the local minimum what happens. And also in the SVM chapter. Lagrange lot multipliers have been used a lot, and I hope you're comfortable enough to use it, like in the next slightly different SML model than what we have seen exactly. And then pretty much in parallel, we started let's say the supervised learning, like two stereotypical supervised learning type of problem. We talked about regression a lot. In particular, we talked about linear models for regression, and then we talked about the Bayesian version. Of regression. That not only just put a prior on the weights, but also we marginalize over the prior when we do predictions. That's obviously chapter 3. Chapter 4 is about classification. There are 3 big blocks of content in there. discriminant functions, generative models, generative classification models, right? And discriminative models. So these are motivated by decision theory and the different underlying probability distributions. Within these, we basically obtain logistic regression from first principles. We have also been Bayesian about this, right? So we looked at Bayesian logistic regression. Despite much later, we actually looked at it along with the GPs because that's where we introduce approximate inference. And then we kind of changed pace a little and started looking at basically different type of models that could potentially do both regression and classification. So examples of those include neural networks, we also looked at graphical models in quite some detail. And there's kernel methods. So in kernel methods, we actually started by defining the kernel. And what we introduced there was actually kernel linear regression. And then, well, chronologically in the class, we introduced support vector machines as a way of learning the discriminant function of classification tasks with a kernel. But SVM can also do regression as well. On the contrary, so in Gaussian processes, the most natural thing to do with them is to perform a regression task. And then we can use the mapping function to construct to do classification as well. So in terms of, I would say, broad level connections, so these are any of these neural nets can do classification and regression as well. In fact, in graphical models, we can think about it as basically doing classification or regression depending on whether the variable we're trying to compute the marginal or conditional on is discrete or continuous, right? So I'll do that. And the different variants of these methods basically, connects to different variants within the regression and classification constructs. Once we have the vocabulary of this sets of problems and models, it sets us up to think about a lot of other it sets up us to read lots of recent literature that could be sort of as classification or regression. Right. So besides, this is not all we have covered. We have also covered a number of, how do we say, non-standard machine learning problems that are not supervised learning per se. Right. So the two groups of things we talked about were mixture models. And clustering problems, including k-means. Gaussian mixture, and you did basically general mixture model or a more general case of deep mixture model with the exponential family in the homework. The other cluster of things we talked about is dimensionality reduction. In particular, we talked about PCA and autoencoder. So nonlinear dimensionality reduction. These are a small selection of a large number of different approaches. Right? So this opens up like possibilities for us to ask questions like, okay, so there is kernel PCA. It's a valid question to ask, right? Can we map the data to some kernel space and then do PCA? And would that generate better latent dimensions? So that's sort of covered in the book. It was in last year's homework, but this year we didn't hold you guys responsible to it. Yeah, but you, and then there is also probabilistic PCA, for example, which is, you can think of it as somewhat Bayesian. So among these green bits, you can essentially combine different ideas to obtain new models or new variants of models that are better sort of emphasize one or more aspects of the model. If you want to enforce priors, or if you want a probabilistic output, or if you want a good optimization program that are somewhat quote unquote easy to solve. So this sort of is a menu of items to choose from. Outside of that, we also covered a bunch of ideas that can be used across these problem settings and models. For example, in terms of how do we do the learning? We started with analytical solutions for maximum likelihood estimation or maximum a posterior estimation. So that was, remember chapter 3, and the normal equation and so on, and the normal equation with a regularizer term. We also talked about fairly late in the class, Laplace approximation. That is when we have posterior that looks intractable. How do we make it simpler? Of course, gradient-based optimization has been used a lot in all sorts of different models. These are the possibilities. We talked about sampling as the way of doing inference, paradigm for doing inference. We talked about so the sum product algorithm of fair factor graphs, or message passing as ways of doing inference. Yeah. So we could use, for example, this bag of tools to then perform learning and inference on many of the green bits of this plot. In addition, what else have done? We did EM, expectation maximization, which is a neat way of partitioning the space and to essentially coordinate descent. We also talked about generalization, or how to think about generalization as the first step to think about whether an algorithm is correct and how within finite data how correct it is. So that's pretty much all of what we learned in this semester, drawn on some sort of mind map. Your own mind map may be different. So I hope just talking through them will be somewhat useful. And it might serve as a, I guess, a refresher of the past 12 or more weeks. The next, so I wanted to ask if there's any questions about the content. Let me see. Okay, I see there is a chat coming in. Let me open it. Pretty slow. Right, Kylie said, oh, are you seeing the slides now? Hopefully the technical glitches is gone, or try getting out of team and getting back in. If there's still problems, yes, great, shout at me. Just unmute and speak is fine. So the next speech, in the next speech, we're going to talk about, right, so debugging learning algorithms, what to do. If you're not sure if you're getting the best or even correct performance, travels a lot. These slides are all borrowed. They are Andrew Ng slides from Stanford. So if you prefer hearing from Andrew Ng from it, feel free to, I guess, tune out from this. But there is value. I feel, well, these are well-trodden advice being given by Andrew Ng and many others. There's probably value in sort of packaging those inside our class as well. And this chunk of material is not very mathematical at all, but it is some of the hardest material to sort of understand, grasp, and apply. A lot of times precisely because there is no mathematical recipe that we're talking about. And of course, these are advice. They are not sort of, if you have a linear regression model, you do this. There is lots of discretion, ingenuity, and judgment involved in actually being able to apply them. So there are three parts to this. One is diagnostics, the other one is error analysis, and then the third one is, if you face a new machine learning problem, what would you do? Or how to get started? So here's a motivating example. Suppose you're building a classifier to classify spam email versus non-spam email. Right. And you choose a small set of 100 words to use as features for classifying spam, rather than 50,000 words in English. So, okay, here's a bit of a notation. So why is the label spam or not? X is features or input words, essentially. Theta is the logistic regression weights. As you can immediately see, once we go out of the Bishop book, even the terminology is changed a bit. It says it's Bayesian logistic regression. What it says, it's essentially logistic regression with a regularizing term, which is equivalent to putting a prior on theta. But what it does is it's solving the map estimate, maximum a posterior estimate for theta, rather than sort of derive a posterior distribution for theta, right? So this analysis, not doing P of theta given all the x's and all the y's. So the key thing here is you're faced with a challenge, right? So apparently you're getting 20% error rate. That's too high. You expect better. So what do you do? So on the top is just the objective function written out again. You can sit down with a piece of paper and write down all the possible things to try, right? In this case, oh, my error is too high. So I can get more training examples and an even smaller set of features. Or I can try a larger set of features or changing the features, like, for example, include header features versus body features. And then you're wondering whether your gradient descent has gotten to the bottom of something yet. And whether you should be using gradient descent at all, whether you should try Newton's method first. Oh, and then what is lambda? Shall we go search for it? Or maybe swap out the classifier altogether, use the SVM instead, or neural network to that end. So this, you can try each of them one by one. Trying some of them is a lot harder than others. For example, if you don't already have training data lying around, gathering that if you're in production environment may take a few days, or with approval and so on may take even longer. Changing your set of features seems easy. Devising new features is also somewhat easy. Changing your optimization paradigm may be easier. And then searching for lambda C are pretty much sort of standard. These are easier fixes. But there also could be sort of a combination of things that are wrong. For example, a smaller feature and a different lambda could get you to the right point. So what do you do, right? And so operations like this makes machine learning seems like an art rather than engineering discipline. Right? It seems like, oh, I can try a lot many things, and it's largely a matter of luck whether we end up fixing what the problem really is or not. For those of you doing research projects on empirical data set, such as in computer vision, where in papers you regularly see there's a giant table comparing our approach to 10 different approaches. And because it's a published paper, you generally expect to see that their approach works best. And you're like, how did they get that? And why? Yeah, it's not easy. So here's an alternative approach is, and the proper engineering approach, right? For example, if your device, let's say if I have a blender at home and it doesn't work, then I can essentially measure different parts of the device to see, or observe different parts of the device to see what can be possibly wrong. And that's how you find a bug. For example, is the power supply okay? If not, then I can, for example, swap in some parts and see if they run okay. And I can actually also take a multimeter and measure different parts inside the device to see if the power is properly supplied or if the motor is working and so on. So that's the idea, which is run some diagnostics. In this example, we're going to use bias variance as the diagnostic for our first one. And hopefully that shows us what the likely problem is, and that gives us a direction to try. Suppose you suspect the problem is either overfitting, let's say, to a set of emails that are too similar, or too few features to classify as spam. That basically is high bias. So the bias and variance trade-off could exemplify themselves very differently in the age of over-parameterized models, but these principles still apply. So the diagnostic we expect right early on in the SML book, when there's high variance, training error will be much lower than test error. And when there's bias, training error will also be high. Basically, we can't get the training error down, then the model is probably not expressive. So here are the pictures. If our desired performance is in red and training error is well below the red line, but test error is well above, then this is a sign for high variance. And in this curve, the test error seems to still decrease as training data set size increase. Then maybe I need more training data. Right, so then the goal is to shrink the gap between training and test. If we're at this other scenario, then the training and test error are pretty close, but they're quite far away from desired performance. And this is, well, maybe prone to high bias. Maybe I need to change my feature set or change to a more expressive model, which is nonlinear. That could help. So by observing these learning curves, basically performance versus number of training examples, we could essentially, in the first 4 options, rule out half of them. And we can go after the next 4. But let me, yeah, Vikram said he doesn't like, right, these are stylistic features. Actually knowing what is a big gap is not obvious. It's not always obvious. And knowing where your red line is also not always obvious. Imagine a scenario where you might have, okay, so we have somewhat red. Okay, suppose our red line is here. Oh, green now. Okay, suppose our test error is here in green, and then my training error is here in blue. Is this a big gap or not? And then maybe my desired performance is here, but I can probably live with it if the desired performance is here too. Then you're like in the like unclear land again. So the scale of the y-axis does matter a lot. Not always clear. This kind of stylistic features. That is a good question, Vikram. Yeah, sometimes, well, when you are at problems like these long enough, you sometimes know whether the error is like has the potential to go down, but it just doesn't budge at all. For some domains, you can expect, for example, 30% error rate is acceptable. For some domains, like even 5% is too high. You can think, well, that should be easy. Now, MNIST, for example. Anything similar to MNIST should have a lower, not so high error rate. I don't remember what the running error rate is for example, MNIST fashion data set, which is slightly harder than MNIST, but I don't expect that to be 30%. You can, of course, ask the domain expert how good would they, like, what is the error rate for them to not be worried to outdo whatever they already have. Okay, we talked about bias and variance. Now let's get to the guts of the algorithm. So how do you know whether you should question your choice of gradient descent or whether we have running enough versus models and hyperparameters? So the disclaimer is, unfortunately, there is no like universal diagnostic toolkit, right? So learning curves of different kind are usually the go-to. That is true. And then beyond that, we really need to think, actually. And we can, right, in the spam example, we probably want to look at the errors per class. That's quite a good commonly used diagnostic as well, right? So it says, well, this gets 2% of errors on spam and both spam and non-spam. That means 2% of your correct, like legit emails get sorted into spam. That's not good, right? And if you use a SVM, it gets, despite it's only a linear kernel, it gets about 10% error on the spam and a 0.1% error on non-spam. Maybe that's more acceptable, right? So it's getting rid of 100 spams per day for me, but I see 10 that slip through the filter. That's not ideal, but it's better than losing, let's say, 2% of my legit emails. So what do we do, right? So in terms of whether gradient descent have converged, this is similar to the question that Vikram was asking. By just eyeballing it, we wouldn't actually know. In this case, if we can afford it, we spend so much time sweating about these curves, and moreover, we have swept through, for example, different test data set, we might as well just have one thread run gradient descent for much longer. Come back tomorrow and see where our point is. It is quite hard, right? Because when in any optimization problem, like especially neural networking, in the beginning there may be a lot of change, and then after a while the change become really small. But if you could essentially zoom in onto this area and blow up the y-axis, then it will also look like it keeps changing. You could do statistical measurements, of course. A lot of cases when we're doing diagnosis, our brain is doing enough work that we don't necessarily want to do like statistical measures. It's hard to tell, right, for the objective. So if you can put another curve onto the same plot, then that might help, right? For example, this is training objective, right? So if we can measure the same objective on test data, maybe that could help us, could help tell, or not on test data, but on validation data. Then we can see if the objective on the validation is improving. Then that gives us at least two curves to contrast, which is more helpful usually. Right. So here are a few other common ideas for this type of, say, spam classification type of classification problem. So it says what we care about is this alpha theta quantity, which is weighted accuracy. For the classifier with parameter theta, right? Where the weights, right? So these are WIs are weights for spam and non-spam. And then you say, yeah, that sounds reasonable, right? But then you ask yourself, but this is not what the learning algorithm optimizes directly. This particular, I guess, phenomena happens a lot. Where the learning algorithm optimizes a surrogate, but our performance is measured by, some weighted accuracy clicks, or like whether people want to read the text that you generate. But it's hard to directly measure the outcome. Therefore, we sort of optimize a surrogate. Excuse me. Right. So the J of theta was exactly the objective that we saw before. Now it just has a name called J of theta. And then for SVM, here's the optimized stock standard formulation for SVM. And you're wondering whether you have like the correct hyperparameter C, which upper bounds the proven weights and controls how many examples are like incorrectly classified, right? So what do we do with this? Because, right, so in this case, in this example, in SVM, we talk about linear SVM. So linear SVM and let's say logistic regression are both parameterized by theta. And if our feature is, let's say, phi, then the discriminant or the class posterior are both something like a function of theta transpose phi, right? That makes SVM and logistic regression almost directly comparable. In a sense, the optimization is done differently. The function f is different. Right? For logistic regression, it's the sigmoid function. For SVM, it's the psi function. Right? And then there's regularizers that will drive, for example, the logistic regression regularizer will drive the theta to a different spot, right? Same as is SVM. So as we said about 2 slides ago, SVM outperforms logistic regression in the weighted accuracy. It sort of makes more mistakes in the undesired class and like it doesn't throw away your good email. So there's that. Excuse me. Then we want to ask, okay, given that we observe this, whether the objective function is following the same pattern or sign. Right, so then that leaves us with 2 potential outcomes, right? So we could evaluate this objective function. Case number 1 is that SVM outperforms has lower error and also, well, we're maximizing, so higher objective function. This means that despite Bayesian logistic regression directly tries to maximize J, this objective function, it's not maximizing because we just obtain some other theta from optimizing other objective, and that theta SVM is getting a better loss or better objective than the logistic regression. So if this is the case, the problem is with the optimization algorithm. The converse, if J of the logistic regression is actually larger or better than the corresponding J from a random J or from SVM, then that means, I would say, well, it says Bayesian logistic regression succeeded at maximizing J or theta. It's a bit strong. It means it at least didn't fail, obviously. But what's the problem here, right? So the SVM solution, which does worse on the objective function, it actually does better on the weighted accuracy, which is closer to what you possibly actually want. This means that we probably shouldn't be optimizing J of theta. If we care about A of theta, then we can directly maximize that, despite it's not differentiable and so on. Or try different objective functions. All right, I hope that makes sense. So to summarize, we saw two example diagnostics. These are diagnosed with learning curve. And then these are diagnosed with, say, objective function value, J theta versus A theta. And you have all the background knowledge necessary to do this. You just have to, like, if you do use machine learning, you just have to get used to doing this a lot of times, and then you'll get sort of better at it. Another thing I would just like to share off the cuff is for hyperparameter optimization, also for searching, like, say we need to search for C for SVM. Yes, you could do what you guys did in assignment 2 and use the Bayesian optimization, right? Basically Gaussian process to arrive at a good value. But usually if your hyperparameter is very low valued, like low dimensional, like this 1 or 2, it's better to do what's called grid search to make sure you didn't miss anything. So the thing in grid search is you first need to decide, you basically need to decide the range, let me say. And step size of the hyperparameters. What do I mean by that? Is depending on how you set up your objective function, whether it's normalized by the number of data points or not, you need to have a sense of the actual numeric range of these functions in order to know whether, like, if you have two terms that trading off with respect to each other using lambda, then your lambda needs to include a value that more or less puts them on the same sort of same order of magnitude. If they are, for example, always 3 magnitudes difference apart, then the part in the objective function with a lower value will never matter. Right. So first is determine the order of magnitude. And then yeah, and then you need to fix the two ends. And then you need to pretty much decide whether you need to search in log scale versus linear scale. Right. An obvious case for setting hyperparameters in linear scale is you can put your objective in the form of, let's say, lambda times J1 of theta plus 1 minus lambda times J2 of theta, where J1 and J2 are comparable sort of numerically. In log scale, I think sometimes the C in SVM is a good example where you need to, it's better to search in log steps because what you want is, let's say, from 10 to the minus 5, or let's say 10 to the minus 5 to 10 to the plus 3. These, if you search in linear scale, you will ignore the smaller numerical values readily. And let's say if you decided that this is the range and you're doing log scale search, sometimes my research students or project students in my group will come back and say, oh, I did this. Let's say this is the error. And this is maybe value of C. I tried whatever, this is 10 to the minus 3, and this is 10 to the plus 3. You keep dropping. Therefore, we're picking 10 to the plus 3. Done. And our response, like not just me, but people I've co-supervised a lot, we usually say you should go a few more steps beyond 10 to the plus 3. You should expect to see a ball shape before you decide where the bottom is. Anyway, these are plain common sense. And this is also to say that there is a lot of details to get the practice of these algorithms right. Right. So quite often you need to come up with your own diagnostic to figure out what's happening. Whether it's when it's learning well, why it's learning well, when it's not learning well, what might be wrong. So when you're writing research papers, diagnostics help convey insight about the problem and justify my research claims. And these, I would say, the reasons why something works is a lot of times more useful to contribute to a body of human language or engineering knowledge about machine learning in a certain domain than just to say, my algorithm achieved 5% error rate and it's a lot better than others, without saying why. This is exactly what the next bullet point says. Here's an algorithm that works because of component X. And here's some justification or evidence for that too. Any question about this part? I see Fei Yang and Vikram has had a discussion about the weighting of final exam. Yes, it's at least 35%, unless like your quiz score is redeemed from it. Each quiz is 2.5. So if both quizzes redeemed from it, then it's maximally 40%. Right. Okay. So let's look at one machine learning problem. Let's say we want to recognize faces. Is the face of the current person in the picture one of the 100 known faces in my database, right? So and here are different, it's a, let's say, yeah, face recognition is actually not that easy, right? You really need to locate the face, and then you need to calibrate the face so that it's more or less front-facing for you to do a reliable match. And better skill, you had better, like, in order to rectify the face, you need to know where the eyes and mouths are, and if there's, like, whether it's wearing glasses to sort of downweigh maybe the appearance in the eye area and so on. So here are the components. We first want the person to be on a plain background, remove background, and detect faces. After detecting faces, put in the box, circle the eyes, nose, and mouth, and then feed it to a logistic regression or neural network, let's say. Out comes the label. It's contrived. It's not super far from the important components, right? So suppose you have an overall system that's 85% accuracy. One way to justify like what you did is good enough, or also to understand what parts of the system work better or worse than other parts, what you could do is, suppose you have training data, right? And your training data might have ground truth eyes and nose and face marked out. You can then have an analysis that attribute the overall error, 15%, to each of the components. In order to do that, assume you have the ground truth. You can plug in the ground truth for each of the components and then see how accuracy changes. So here's what happened. So I plug in some ground truth clean image with background removed. It didn't change at all, right? Almost didn't change at all. 0.1 improvement is negligible. So pre-processing don't, like it's not hurting the performance. And then if I plug in ground truth face detection, it jumped up by 6%, right? So face detection arguably is one of the, let's say, easier problems. It's actually one of the early successes of machine learning. For those of you who, most of this class is probably a little bit too young, but when you were little, there were like these handheld cameras on the market that show a green box. That's before we all ditch these handheld little small cameras and start using our phones. It basically locates the faces, and they're mostly pretty accurate. But turns out that face detection, like not having the perfect face detection hurt accuracy by 6%. So that sucks a bit. And then the other changes that need to be done on top of face detection because of the diagram, right? So from 91%, if I know where the eyes are exactly, I get up to 95. And if I further know what the nose is, you get up to 96, 97, and so on. So it seems like face detection is the most significant component. And on top of that, eye segmentation is the next most significant. So if you are building, say, if you work for a camera company that does this, and you show your boss or decision makers these, that should be a solid backup of what you're doing and why you're doing so. And for example, why it cannot be easily improved more. I will also say that we talk about performance measurement in our class and also in other related class a lot. Setting up a proper evaluation in a, let's say, real or practical setting is not necessarily that easy. So Dan Andrewing's slide makes a distinction between what he calls error analysis, right? So it's basically, you see how better we can be, how much better we can be if we have better input or perfect components. Ablation analysis, ablation study or ablative analysis tries to explain the difference between some baseline, some much poorer performance and the current performance. Basically, I did these tweaks, and it's now 85%. A lot of times you need to justify saying, if people just run logistic regression on the image, what will happen? Is the result of that 60% or say 83%, in which case the fancy processing didn't do much. Suppose we go back to the anti-spam classification scenario. So initially you were not satisfied with performance, and as a good engineer, you went back and added lots of clever features to the logistic regression, right? Spell correction, sender host features, email header features, text, Java pass the JavaScript, and so on. Doing all that took you 2 weeks. And you run it, it did get better. And then you wonder, how much did each of these components help? Should you keep all of them, or should you actually drop one of them? Maybe it will actually improve the performance even more. So ablative analysis is basically removing system components or swapping in and out different components at a time and see how much worse it gets. So the overall system accuracy is now 99.9%. That's great. Right, the baseline is 94. So between 94 and 99.9, you remove one of these features one at a time. So the gap between spell correction is only 0.9. That's not so big. The gap between the overall and the sender host features is about 2% or 1%. Same with the header features. And the email text parser feature seem to help a lot, so it's 4.9%. JavaScript parsers seem to help even more, given how much rich text message we're sending. So this is about 5.4%. Right. So the conclusion is right. These two probably help the most. And then you can try to build a system with just the baseline feature and the email text parser, and maybe the JavaScript, and see how much it gets. So that's about ablation and error analysis. The last part of these Stanford slides are on the two different philosophies of how to do it, how to get started on the learning problem. Approach one is, okay, here's a question before we get dived into the depths of the next one. If we remove a component, do we need to train our system from scratch again? The answer is yes. So this is to say, what are we changing, right? So we have, let's say in here, the components are features. We are essentially looking at input, and then learning algorithm. And then this gives us some sort of model, let's say stored in a Pico file. And then we essentially run test data on it with the corresponding feature. If we test the effect of different input, we should keep the learning algorithm fixed, but retrain the system. So if we're learning, let's say, logistic regression, then with or without a certain feature, the weights of other feature would have changed. So error analysis or ablative analysis is different from just handicapping a classifier by removing some input. I hope that helps. So suppose we were given the spam classification task today and asked to deliver a prototype. What should we do? Approach number one is to carefully design the right features, carefully think about what's in spammer's head, what are the linguistic features in all spams so that I can capture them, and what are the email encodings and different possible email formattings that are commonly seen. Collect the right data set and then design the right algorithm. And then we implement it after months and hope it works. The second approach is build and fix. Implement something quick and dirty. Oh, yeah, I can get a simple parser to grab the words out from emails, and then I run logistic regression to it and see whether it works. So the second approach will also often get our application problem working more quickly, and it's faster to see some results or impress your boss, your clients. I wouldn't say don't do our approach one, definitely, but so the later iteration of this same Stanford class has a quote, which I like. A well-running machine learning system is a rewritten, poorly running machine learning system, meaning approach two, build and fix. So when Andrew say contribute to basic research in machine learning, it is true that approach two would not lead to research contributions very quickly. But on the other hand, it does generate good baselines and solid baselines that are debugged and fixed. Even when you're trying to generate research results in machine learning, important to have the right insights that are new, rather than trying to have all the insights about a problem, which I argue is impossible. Premature optimization is sin. For those of you who have like learned software engineering, you will know. So back to the face recognition problem. Very often it's also not clear what parts of the system are easy or difficult to build, and which parts you need to spend a lot of time. So if you actually had to build each of these components for that phase, probably will take you a long time before you get to the actual logistic regression. The step one of design a learning system is first to understand the data, to know what to try first. And the only way to find out what needs work is to implement it quickly, find out which parts break. And I believe that. For example, right, so there are lots of examples in the research and practical literature. Here is, if we want to build a mail delivery robot, that's the goal. So the robot needs to sort of grab envelopes or mail, pieces of paper, so they need to manipulate. Okay, fine. They need to avoid being able to avoid obstacles. Therefore, it needs some navigation possibility. And then it needs to detect envelopes and objects and mailboxes. Then for that, right, so if we're like essentially trying to rebuild the world around the robot, we need color invariance, lighting invariance, we need three-dimensional ability to reason 3D. And then after that, we think about, there's this cool literature on differential geometry of manifolds in 3D. And then complexity, we have some neat theoretical results that we can plug into that. So all of this is sort of getting too complicated too quickly. On the other hand, if your task is to build a mail delivery robot, do the simplest thing. The robot's ability to perceive the world may be wrong, but they may get the job done. I guess so looking back on the three parts that we covered, the time spent coming up with diagnostics for learning algorithms, usually time well spent. In fact, another really powerful diagnostic to your new fancy learning algorithm is often usually what toy data do you feed it to see that perfectly suit your learning algorithm. If your learning algorithm at least work on the toy data, then it has a chance of being correct. So first of all, designing the toy data requires thorough understanding of the learning algorithm, which is usually not easy. And then if it works on toy data, then that's a great step. Then you can ask what's different between the real data and toy data, and that will give you a lot more like informative diagnostics too. Right. So you can decide, right? So we talked about diagnostics, we talked about error and ablation analysis, and there are two philosophies about designing and implementing. I'm not saying always do quick and dirty diagnose and fix, but maybe start with that. And then in the middle, like in the iterations, think about your design choices very carefully, and then implement them. So they can be used in combination as well. I also highly recommend the later iteration of this machine learning advice lecture. Christopher Ray is really great in a large variety of machine learning applications. So here are, he outlines 7 steps for building a machine learning system. We have not, in this class, we've including this lecture, we talked about these a little, and then in this class we talked about repeating a little. We haven't actually talked about the important steps of before machine learning, like basically what constitutes data is actually a big question and usually garbage in, garbage out. And then looking at each per processing step is important. Creating training tests and development splits to avoid data leaks is also very important. For example, if we're doing time series, we shouldn't sort of have training and test data sort of interleaved in time. That way we're training from the future. That's not good, right? Which leads to overestimation or misestimation of performance. There's lots of other, I guess, very practical good advice in also online, but these two deck of slides I would recommend. I didn't pick this second set because it's kind of a lot longer. It does have more pictures and less equations. So I trust you could enjoy at your spare time or over a cup of coffee when you like. I wanted to and talk about the communicating about machine learning to your friends, family who haven't necessarily learned machine learning, talking to your, let's say, bosses at work, and also the press. Sometimes you do get that opportunity. And also, what are the potential gotchas, broader implications and pitfalls of deploying machine learning algorithms? So this particular paper, I believe, is in Europe's. Yeah, it's definitely in Europe's. I forgot which year. Likely, yeah, let me not speculate. Anyway, so it's sometime post 2010, between 2010 and 2020, I would say. It's a paper from a bunch of yeah, Google researchers, and I feel like this figure from their paper is very illuminating, right? So when you actually do machine learning, suppose you get a job at Google, which is pretty exciting because you get to do machine learning, have like on lots of real data, and hopefully in a way that helps people. This is what your software component stack look like. Your machine learning code is a tiny little bit among many other infrastructure code, right? Let me see. So you have training data. Now it needs to be verified because this is the real world. It doesn't come in a spreadsheet. It comes in real time, and sometimes it's corrupted. So you need code for that. You want to train, or if you're just predicting, you're running on a server farm, you need code for machine resource management. And within the machine, you need process management. Once you have the data, you need to sort of like you collect the data, you verify it, and then you extract the features, and then you feed it into this. With all these complex code, you also need some configuration management code that sits over here. For example, if each of these code is a Docker, then you need a Docker orchestration or remember all that. And then there's suppose you're just doing a prediction, you need a serving infrastructure. So if you're serving up web searches, you need some servers to hand off different queries to different machines and then make sure that it returns. These are very non-trivial, and you need monitoring to see that all of these is up. This paper talks about even if we write the correct machine learning code, so there are a number of challenges that leads to what's called technical debt, right? Meaning deficiencies in different technical aspects. Its machine learning code are not write and forget things. So we need to monitor its accuracy. If the data has drifted, then we need to retrain. We need to monitor the data integrity. So if the data characteristic or format changed, the machine learning code needs to change. So there are various, let's say, dependencies and links among these software components that are not usually managed easily or not easily. Yeah. So, and imagine if you're in the engineering department, let's say if you run Google search, then that team might have hundreds of engineers, and you have somebody leave and a new person comes in who tries to wrap his or her head around this whole jumble. If they may miss some link, then the results could be fairly disastrous. This is to say that actually using machine learning, if you are, let's say, one day the head of product in some company or government department, essentially your team will need to be mindful of all of the other components that this machine learning component talks to and being influenced and influencing. Switching gears, so last year I heard a very good talk about how you talk about AI to a non-technical or like non-AI and machine learning audience. Of course, you can choose to talk about it or not to, right? When you say I'm with family, friends, I only talk about network stuff, that's fine. So in public communication, AI is still often conflated with machine learning, which is a strict subset. For those of you taking the AI class, you will know. There has been real progress in machine learning, driven by scientific advances and larger data sets and cheap and easy compute. These advances are narrow, so the current machine learning systems, including GPT-3 and beyond, are still doing pattern matching and pattern reproduction. And it does not deliver the grand dream of AI, of having, let's say, human level intelligence, despite it can be perceived to sometimes make sense, such as chatbots and so on. So the advances in AI are really exciting, but they're not magic. This is also to say that I mean, I get this from my friends too, where they say, well, will AI actually destroy us or so on. So long-term speculative concerns should probably not distract us from near-term worries. There's lots of near-term worries, as we can see. Machine learning algorithms not working, they're brittle, they have technical debt. They actually deploying them in the real world affects our employment, affects our well-being, long-term well-being prospects, our climate, and so on. Here are some of the near-term worries. Example, this was an early but well-known example. Google photo classification. A software engineer found that the classifier mistakenly classifies his dark-skinned friends as gorillas. After 3 years, Google simply removed the category called gorillas. And there is no good fix. You will say this is a training data problem. It's not exactly purely a training data problem. You say the algorithm appears racist. That's certainly true. That's how. I think the whole field is still trying to address problems like this, how to potentially prevent and mitigate harm. Well, I say this with a vested interest because I currently lead the HMI project. I try to say that, well, reasoning about harm is actually hard and try to design an algorithm that works better. Otherwise, might be slightly easier. Here's another example. There is, so the field of recruiting and human resources apparently has gone through quite a revolution with machine learning. Basically, before this, the screening of resumes are done purely manually, and that's a very labor-intensive and time-consuming, resource-intensive process. Since people have figured out that you can actually read resumes and just, I don't know, classify using keywords and so on, that has taken off as its own industry. That has gotten a number of infamous press release coverages This is one of them a few years ago. Well, big firms gets into this bad press. The small firms who actually sell HR services don't, but we should also be mindful. Amazon scrapes their secret resume screener because that perpetuates bias of there are more men than women, let alone I think non-binary gender people in the software or internet industry overall, especially in technical roles. What the software end up doing is it end up learning that certain sort of words that are not explicitly associated with female names or gender pronouns, but things that are subtle. For example, names of women-only college was given a negative weight and so on. So that's not good. On the other hand, so there are basically pros and cons, like the two sides of the coin about this automatic resume screening. So we know that people have biases. Like you can argue whether the algorithm's bias is actually worse than people's bias, which is not a computer science question in its own, right? You could also object to the fact that even people or the human recruiters have biases. Using an algorithm to enforce bias is strictly worse because it removes, let's say, the human agency in the whole process. Let's go not get into that, but let's just be aware that there's these kind of issues are complex. There is no easy answer to say that, well, algorithms are biased in hiring, then let's not use it at all. Another question for Qingyu. Thanks for keeping them coming. Other people are welcome to chime in as well. Why is machine learning blamed for its bias, such as racism and gender discrimination? The algorithm you learned are pursuing accuracy, which looks neutral. Yes, is bias data the problem? Great question. And there is no short answer, but I can tell you that accuracy is not neutral. Here's why. First of all, like earlier today, and also sort of throughout the semester, we sort of said that ML algorithms, right? So ML metrics or objectives, they're surrogate. They are surrogates to what we want in the real world. They're not sort of the goal in itself. For example, in this hiring case, let's say the goal is to build better products that people will actually want to use and bring value to them. There are historical sort of biases that have persisted in the workforce. It has been shown that product testing has been mainly done by men, like or with male subjects. Perhaps, for example, so there's not enough female developers nor subjects to actually inform how this product could be better built for either, say, female gender or some other underrepresented group. Right. And then when the algorithm tries to find job candidates that look like the current pool of workers, of course it's going to find mostly men. And that don't necessarily lead to better product because we said accuracy is not the goal, right? Like, if we get the algorithm to find resumes that look like the current set of employees, and maybe we even measure it as the employee screened by the algorithm will eventually pass their first year performance review. That's also a surrogate. It's not necessarily the better product. In fact, I was just having this long discussion in a research seminar today. about the harm of benchmarking and surrogate metrics. Unfortunately, this is not a problem that engineers can solve alone. One recipe for addressing the limitation of surrogate metrics, or like accuracy as a surrogate metric that's certainly not neutral, is to have multiple metrics and also really understand what are the true underlying objectives that are not necessarily quantifiable. And for that, people like us will need help from social scientists or people with social science background to say, well, what you care about is this. Here are 5 surrogate metrics. And after these 5, you need to sort of look at these aspects to see if it's broadly aligned. There is no like unique tick mark that a machine can give out to say, oh, check, you've achieved the objective. So changing the world is hard. We're building systems that are interacting with people, or social technical systems, in which technology such as SML is not like the main solution. Yeah, what should I say? I would say that, well, despite that, the boundary of techniques, well, basically the space of technology solutions is still so interesting, and it sort of empowers us to sort of talk about different technical components as part of the solution. So we should keep learning and pushing at the boundary. And I hope some of you will enjoy projects, research projects, or even a PhD in this area. So that's all what I have to say. Gonna pause a bit for questions, and I'm just, as I said, we won't meet on Monday, and then I'll show up again on Wednesday, and the plan is to talk about some of the problems in the sample exam from last year. And I was hoping that people might want that. If, like, I can start with a few questions, and then maybe we can just do a like free-form Q&A. If you want something else, so post it on Piazza or message me or leave a note here. I'll be happy to accommodate. And then in week 13, the tutors are going to do drop-ins while I finish, the whole team finish sort of polishing your exam instance for this year. Okay, Vikram asks, yeah, what weapons do we have for combating the parent bias and unfairness? Good question. So what should I, let me share, so there's a whole community around it these days. Within SML, I would say fairness in classification or fairness in machine learning has become a proper subfield in itself. I would say there are some well-known results. It shows the very notion of fairness is contested. There are at least 27 different kinds of fairness, and you cannot satisfy them all. Moreover, there are about a few different types, and you can only there are some axioms that preclude, like, to show some are contradicting with each other. Just to give a sense of, while I'm digging up the reference. So there is a notion called statistical parity, which is similar to what's called affirmative action in the US. Basically, if there is X fraction of this population, then a fraction of the selected, let's say if we're doing university admission, and there is, let's say, 5% of blue people in the population. Then 5% of university students should be blue. That's statistical parity. Another criteria is called equal opportunity, or which I can't quite recall the precise definition of in machine learning literature. But there's a number of other cases that look at, for example, false positive rate for different groups and false negative rate for different groups, and try to equalize those. As you can see that the choice of these fairness objectives, there are many different algorithms that sort of trades off these fairness objectives with accuracy or some these standard surrogate metrics. I would say, right, so there are certainly toolkits like this possible, but when you're really using it, as some of, so for example, Gradient Institute is one of our research partners. What they've been working on is to really get their clients in government and commercial settings to tell them what they want, essentially. Like, what metrics do you really care about? What kind of unfairness are you trying to mitigate? Which is itself not an easy problem. So I'm right. After we hang up, I'm gonna dig up, for example, two very well. Actually, there are 3 papers about different fairness criteria, and their conflicts with each other. They're well cited. You're welcome to take a look. Another thing I'm happy to share about myself, or the research team I'm working on, is I'm going to I plan to attend this Fairness, Accountability, and Transparency conference, which is like the premier venue about these problems. It's going to happen sometime after the final, so after grading the exams, I'm going to fly off to Korea and basically attend this conference and get the latest of this whole area. And the contribution me and my team had in this particular topic was a transparency tool, accountability tool for data pre-processing. Let me see if I can find a picture to share with you guys. There. Is there a search feature? Okay, I'll stop my screen share. Then find the file from my computer to share. So that. Right. So I found it. Waiting for the paper to come up. All right, here we go. Not sure what is Teams. Doesn't share windows very well. Bear with me 1 sec. Fix it. Right, okay, it's sharing my whole screen. Fine. So this is the paper I plan to show you. It's driven by Lydia Lucchetti, a PhD student in the HMI group. What it does is it's basically a visual cartoon of data pre-processing decisions. Again, these are all before any SML is done to it. As an example, so right, go to one of them. So here's a data set. Step 1 is to remove columns that that does something, step 2, step 3. So each of the changes of the entire data set is visualized by color using a small sample of the rows of the data set. So that's why it's called small set. As you can see that, right, these kind of tools are useful for transparency and documentation and accountability only if people devote the time to actually do this, right? So writing documentation is hard. Writing documentation that fully reproduce what it is for the entire intended audience is also hard. This is sort of one step to ensure reproducibility and accountability. What I also wanted to show, right? So here is some fairness results. So we basically compared different type of pre-processing and then measured equal opportunity and statistical parity on some population data set, US, basically community surveys, similar to census. So we showed, for example, basically different thresholds and different ways of filtering out data does have sometimes a large influence on some of these fairness measures, such as equal opportunity and statistical parity. And then the effect also differs depending on which data set, in this case, the states in the US we are looking at, right? So Utah, for example, statistical parity was high to start with, meaning men and women don't have equal income. But in California, it's low, but the variation across different pre-processing operations is actually bigger than those in Connecticut or Utah. So this is a teaser of what we've been recently working on. And it's sort of a tip of an iceberg of what, how to tackle fairness. I hope it's sort of not a comprehensive answer, but some answer. Why is data set not the problem, right? So Qin, you asked that, why is the culprit is the biased data? That's a good question. As I said, the surrogate metric is part of the problem. Historical injustices are the problem, are part of the problem. So fixing data won't fix it alone. Plus, collecting data from minority groups are sometimes places more onerous for the minority groups, which might sort of incur more injustice. I'm gonna stop talking about, right, I guess, fairness and potential harm. It is a very complex and loaded topic. On the other hand, you could flip the problem and try and think, yes, there might be a larger group of other really smart people trying to figure out how to mitigate algorithm harm. You could also find a problem where you can make the algorithm do something better than otherwise would have been done. And of course, keeping in mind the potential harm of the new thing that you're implementing as well. So I'm happy to leave you at that. And maybe I'll see some of you next Wednesday. Let's do it online again because it's a cold and flu season. So many people getting sick. I hope you're not. Good luck with your week 12. See you later. Let's stop the recording. Yeah, I can stop it now.